Welcome to Module 4 on the impact of non-proprietary UHPC properties on structural design. We're pleased to welcome our presenter, John Stanton, professor in the Department of Civil and Environmental Engineering at the University of Washington. John?
Good afternoon, everyone, and thank you for being here to attend after the 3 sessions this morning. In the first 3 modules, we heard quite a lot about the details of the properties of the material from Kingsley, some of the chemistry of corrosion. And in these next 3 modules, but particularly the module 4 now, I think we'll switch gears a little bit and look at the question of the uses of the material in practice. So it's a slight change of tone here. Here we go. I'd like to have a quick introduction, and then we'll talk about the influence of cost on applications. Then we'll look at some potential applications for UHPC. We'll look at the impact of UHPC on what I'm calling structural form, which is the shape of the pieces that you might want to make out of it. And then have a look at the impact of UHPC on design in general at the end. And then we'll pick up some questions after that if there are any. Well, I'd like to start with a little story to depart from the pure science. And the story goes something like this. A dentist, an electronics tech, and a structural engineer walked into a bar. And the barman said, "Oh, I'm so glad you're here. This afternoon, a little green man from Mars came in and gave me a hunk of what he said was a totally new material. He said it's incredibly ductile, it's chemically inert, it's completely non-corrosive, but unfortunately it's quite expensive. And he wanted to know what he could do here on Earth with its amazing properties. Have you got any ideas?" Well, here it is. This is the material. The structural engineer, who was a bit of a loudmouth, said, "Oh, it's ductile and non-corrosive. It's obvious. We should make bridge girders out of it." The dentist said, "Well, have you thought about the cost?" Whoops, where have we gone? "I think we'd be better to use its chemical inertness and make crowns for teeth out of it. You need so little that the cost is really not such a big deal." And the electronics tech chimed in, "Well, if it's also a good electrical conductor, which I suspect it is, its non-corrosive properties would make it perfect for connection terminals on a circuit board." Well, that's gold. It's clear that there are indeed applications for it, but you have to think outside the box and use it where you can take advantage of its properties and not try to use it as a blanket replacement for some existing material. I would submit that the case for UHPC has some parallels with this, and that is the theme that underlies today's talk. So let's take a look at the influence of cost on the applications of UHPC. It's clear that UHPC is more expensive than conventional concrete, and simply trying to replace conventional concrete with it, for example, for a cast-in-place beam and slab bridge, it would provide a more durable structure. It would definitely have a higher first cost because of the obviously higher cost of the material, and it might prove advantageous on a life cycle basis if you work out the reduced cost of the maintenance. So I think the point is we need to look at structural applications that really kind of play to the advantages of the properties of UHPC. We can look at the material cost versus other costs. And the numbers I have here are the cost of UHPC for just the materials are in the range of somewhere from about 500 to 1,500 bucks a cubic yard. The 1,500 is a little higher than some people were quoting this morning. That is actually the cost that we worked out for a UHPC non-proprietary that we used about 5 years ago in some experiments. But that is roughly the range. Of the items, the fibers and the high-range water-reducing admixture are typically the most expensive items. And so those are the things that you need to look at if you're really concerned about the cost of it. The fibers, once again, are typically the steel fibers, like perhaps the Beckett fibers, the steel ones with about a 400 KSI strength. However, that's not the only part of the story. There's obviously labor cost, there's formwork and reinforcement, QC costs, which are possibly higher for UHPC because there are usually more tests to be done. If you're a precaster, there's amortization, depreciation of your forms and the other capital equipment. There's various overheads, sales costs, maintenance, supplies, etc. All of those to throw in. So I think where we get to at the bottom is that with the UHPC, you'll almost certainly be using a smaller volume of UHPC than you would with conventional concrete. And the quotes other costs will be roughly the same. So the outcome is that the ratio of the total costs of the UHPC item compared with a conventional concrete one, that ratio is lower than it would be just for the material cost alone. So I think while some people have become very hung up about the cost of the UHPC on a per cubic yard basis, I think that's probably misguided. And we should look at the total benefits and the total costs. We could look quickly at the proprietary versus non-proprietary costs. I know this is meant to be a webinar about non-proprietary, but I think we have to make the comparison here. If you use a proprietary material, quite often the supplier will provide a representative who comes out to site, and they will take responsibility for the mixing of the UHPC. This obviously costs money, but at present, quite a few contractors are still choosing to offload the risk of the UHPC, and they're willing to pay the premium for to have the rep on site, so they don't have to carry the risk of having the UHPC go bad on them as they mix it. And this may be good for cases if the agency or the contractor doesn't have much experience with the UHPC, they've only got a small quantity, and they will say, hang it, let's just buy the proprietary stuff and have done with it. For the non-proprietary UHPCs, there is something of an entry barrier which is perceived, i.e. you have to learn how to use it, you have to learn how to make it and invest some time and money up front in developing a suitable mix. And a contractor is likely to do that only if they see enough future work to justify the investment, because clearly there's some investment in equipment, in training, staff, and things like that. So this looks like it would be good for jobs where you have multiple projects, if you're bundling several bridges in one, or you've got a large individual job, or perhaps you're a precaster who's going to be making girders or something like that for bridges, and you're going to make a lot of them. So it's worth your while to learn how to do it. Well, if we look at potential applications for the next step then, UHPC has some good properties which we can usefully use. It's stiffer and stronger than conventional concrete. It's tougher and it's more ductile, and it is certainly more durable in terms of things like chloride penetration, as Kingsley Lau was just pointing out. So it's got much better durability in that sense. So the question is, how can we use that, and what are the applications where it would be most useful? Well, if we start off looking at bridges, because this is the ABC Center for Bridges, then some of the opportunities of using the strength and stiffness would be to consider long span precast pre-stressed concrete bridge girders. As we see down here, I think the present record is 223 feet for a single piece bridge girder, and that happened to be in the state of Washington just a year and a half ago. But if we are going to go longer than that, and it seems that the length of these girders is continually increasing, and therefore we will be going longer, a material which has a higher compression and tension strength would allow you to use less of it. That would give you a lower self-weight, and therefore you could go with a longer span for the same cross-section. It would also lower the shipping weight, which would be certainly a convenience. Right now, these very long girders have to use lightweight concrete because the shipping weight would otherwise be excessive. And that lightweight concrete comes with a penalty that it has a lower E sub C, the modulus for concrete. So they're somewhat more flexible, you get more pre-stress losses, etc. And if we could use something like UHPC, which does not have a lower EC, it's actually got a higher modulus, then that would be a big advantage. Now, if you're going to do that, you need to consider some other effects apart from the pure material properties. For example, if the material is so much stronger, then presumably some of the elements of the girder shape will be a lot thinner, and we need to make sure that we can design girder shapes to that effect, so that we can make use of it and not use too much of the UHPC. The second thing is that if you go to longer spans, you probably need higher pre-stress. More pre-stress means either stronger strand, which we don't yet have, or you need more strands. So you've got to have space for those, and therefore the bottom flange of the girder probably would have to be still quite big. A number of people have pointed out the slightly slower set time for UHPC, and this may mean that you've got to have a 2-day casting cycle in order to achieve the release strength that you want. And finally, if the member becomes very slender and skinny, then there are always lateral stability problems lurking around the corner that you might have to deal with. They're perfectly possible to deal with them, but you've got to take them into account. If you look in buildings, then things like columns, you can make them smaller sizes, and that'll make the architects love you. In flat plate floors, there's always a problem of punching shear around the columns, and conceivably we could use UHPC to help out there. There are some rather special cases where a precast beam does not have adequate flexural strength unless you really pack it with compression steel, tension steel, everything. And one of the examples there is inverted T-beams in parking garages. They often struggle for strength. Things like coupling beams in shear walls, which we certainly need high strength, but we also need ductility. And of course, that's where UHPC would be perfect. Now, some of these things, it would mean that we would be interfacing UHPC with conventional concrete. And while we've seen in the past 3 modules that it's perfectly possible to do that in the lab, then out in practice, it may require some fairly careful planning in order to work out how you're going to interface those 2 materials together. If we look at ductility and toughness, where does that take us? Well, seismic applications scream out for ductility and toughness. And therefore, things like the plastic hinge regions of columns under cyclic load, those would be perfect for it. Beam column joints are usually packed with steel and are very difficult to build because of the rebar congestion. And again, if we could use UHPC there, that would be a good application. Things like shear keys between bridge girders, again, the same thing. Non-seismic, if we look at impact loads, if a truck hits on bridge girders, if a truck hits a bridge girder, normally it will break the bottom flange of the precast bridge girder. And if we could make the bottom flange stronger and tougher, then it might be the truck that loses instead of the bridge. And obviously marine impact's the same kind of thing. If you have a ferry impacting a ferry terminal with marine piles, then the same kind of thing is true. It would be good to have the durability there. Lastly, durability, how can we do that? Well, if we can invest in a good material like UHPC to reduce the cost for future maintenance, then it all looks a whole lot more feasible from a cost point of view. And things like overlays on bridges and complete bridge decks, and we'll have a look at an example of that in a few moments. Smaller items like link slabs, joint headers, and I think it was Roy Floyd who showed us an example of a joint header this morning with UHPC, appeared to be doing very well. For marine applications, again, the durability would be a huge advantage. Kingsley Lau was pointing that out. And things like pre-stressed concrete piles, you could mitigate the effects of corrosion if they were made from UHPC. Repair, again, Kingsley talked about that. And even in the civil department, things like pre-stressed concrete water pipes, which eventually have to be replaced when they wear, or else they have to be relined with CFRP or something like that, which is a pretty expensive, labor-intensive process. So I think the point is that there are many applications where the properties of UHPC, other than just the pure strength, can be a real advantage, and where it means that the UHPC is a potential candidate material. So let's have a look at the impact on structural form and see where that takes us. Now this slide here I took from eConstruct from Maha Tadros, supplied it for me. And this is an example of changing a standard 24-inch square pile, pre-stressed, and instead making an octagonal pile of the same outer dimensions, the same 24-inch dimensions, so you could theoretically make it from the same form with a couple of blockouts, but also make it hollow. If it is made from UHPC, you could use essentially the same amount of strand, the same number of strands as you have in the conventional concrete, put those in the UHPC, because the area of the UHPC would be roughly half of what you'd be using in the conventional concrete one. Then the pre-stress will be about twice as high. So instead of 1200, you'd be up around 2500 PSI. You've got half the weight, so it's easier to transport. It's better driving. It turns out you'd have the same flexural capacity. You'd actually have a higher axial capacity with the UHPC, and you'd have better durability as well. So overall, you would have a better performing pile both during the driving operations and during the service life. And again, it would possibly cost you a little bit more because of the extra material, but you'd have to compare that with the potential cost of maintenance or earlier replacement if you use a conventional pile. If we look at bridge girders, this is the Iowa State pie girder, which they used and they built a bridge out of. And I believe the original version of the pie girder was actually developed at FHWA, and this is the kind of second generation one. And what you can see is it took some thought to work out how to make the pie girder. It looks a bit like a double T with big feet on it, the big feet being down here. And some of the features that you have to think about are that you need a draft or a slope, if you like, on the inside here, so that you can lift it out of the form without having to dismantle the inner form here. You do have to fold out or hinge out or remove the outer form on the outsides, but you have to do that with a pre-stressed concrete eye girder anyway, so there's no change there. It has the advantage that it's inherently stable when you put it down. You don't need to support it to stop it falling over like you do with an eye girder. But the things which are different about it are that it has a fairly narrow web here. You need a big blob at the bottom in order to put the strands there, because you need quite a few strands. In this case, I think it's 18 strands they had for a 50-foot span. And at the same time, you can use the top flange here to carry the compression. And if it's UHPC, you've got plenty of compression capacity up there. This has gone one further, and again, this comes from the PCI project, which is being run by eConstruct, and they did something a little bit similar. They went for the thinnest web they could do. The bottom flange still has to be quite big here in order to accommodate the strands, because you need the spans for the long spans. However, the top flange, they made them different by saying we don't really need that much compression capacity in the top flange. And anyway, we've got this full width of nearly 10 feet. And so the continuous flange part only needs to be a couple of inches thick here. So what they've done is they made it ribbed in order to carry the bending loads of having a wheel sitting right there or out here. And by doing that, they can make it much lighter weight and use much less of the UHPC. So the thin web, you can reduce the web thickness because you've got a good shear strength. You don't need all the compression capacity in the top, so you can skinny the top flange down, and the bottom flange, you're somewhat stuck with having a bottom flange big enough for the strands. This is another example of a top flange where they've been using a corrugated metal deck and pouring the UHPC on that, and we'll actually see this picture again. What they were doing is using a steel tub beam and a stay-in-place metal deck form, 3-inch solid on a 3-inch ribs, with the UHPC deck. So here again is an effort to lighten the top flange and reduce the quantity of material in order to keep the cost down. Well, let's look then at the impact of UHPC on design. I think the first thing is you can design the mix for the needs of the application. And this is very true if you're using a non-proprietary mix. You can choose what feature you want to emphasize. For example, if you want to make columns or pre-stressed products, you may want to have high axial compressive strength, in which case you design it for high compressive strength. You might want to have a high shear strength, and an example there would be the girder webs that we've just been looking at, and possibly there you might be looking at putting in somewhat more fiber and be less concerned about the compressive strength. You might want good bond strength, and this would be an example for joints between the precast deck panels, and we'll see an example of that. And with good bond strength, again, you probably don't want to reduce the fiber. You might want to keep the fiber content up, because it's that gives you some of the good bond and tension strength. You might want durability, in which case you can design your mix with exceptionally good particle packing so that you have the good durability. So when you're thinking about the mix, there are a couple of general rules, one of which says that these cementitious materials mostly influence the compressive strength and the first cracking stress, not necessarily the peak tension stress, but the first cracking stress, and the durability. The cementitious materials do not have a whole lot of effect on the ductility. The fibers do almost the opposite. They have a strong influence on the tensile, shear, and bond properties, and you saw that from a couple of I think it was David Garber this morning showed that. But they actually have a very low effect on the compression strength. And if you push it too far and you go up to the 6% fibers, the compression strength actually appears to go down. And we saw that in our own work. And that is quite probably because it gets extremely difficult to mix if you have that much fiber in there. So let's just look at an example. If you want to have a ductile flexural member, an example here would be a plastic hinge zone of a seismic column. Ductility is one of the most important things in the plastic hinge zone. And so you look up in your book and you find, oh, UHPC is very ductile. Let's use that. Well, normally in a plastic hinge, you get cracking of this sort if you do not use UHPC. So the obvious thing to do, perhaps, is to replace this region with UHPC. But if you do that, the UHPC may then be so much stronger than the rest of the column up here, which is conventional concrete, that actually it would drive the failure up into this part of the column, which is exactly what you do not want. What you want to do is to have the plastic bending happening in the ductile material down here. How can you fix that? Well, you simply reduce the size of the element here in the plastic hinge zone a little bit, so that it still has the strength that you need, but it is slightly less strong than this part of the column up here, and therefore you can make sure that all the plastic action happens down here in the ductile region. So this again is a question of putting some thought into the overall design and not looking only at the material properties, but asking how you can incorporate them into a good overall design. So if we go back to the skinny UHPC girder, the question of how do you design the web? And there are some questions that come up there. First of all, will depressed strands be used? They're sometimes called harp strands, and they go up and down here in the web. And if you're going to use those, you have to have enough space for them, and that will demand a minimum width of the web. You may then want to work out whether you're going to have ties in the web or not. Maybe the shear strength of the UHPC will be adequate on its own without having ties in the web. If that's true, then you no longer need to have the cover and the ties and the harp strands in the middle and the cover and the ties on the other side, but rather the width of the web can be chosen based on the strength of the UHPC and shear. So once again, there are some decisions that have to be made which go beyond just the pure material properties. If we take a look at an example of bond, then these are two what we call deck bulb tees, which are a completely precast unit, and they're joined together here by a UHPC joint. And the style of joint there is similar to what you see here. These are in fact separate deck panels. They're not actually the flanges of these guys, but the principle is exactly the same. And you have the bars will project from one panel to the other, and they will lap in the middle, and you'll fill the joint with UHPC. So the high bond strength of UHPC makes it a fabulous material for doing this, because you can keep the splice very short. That means you can keep the joint very narrow, and having a narrow joint is very helpful in terms of having simple formwork. In addition to that, some of the types of joint that we used here previously were welded inserts into the flanges of the members, and they basically did not hold up very well under heavy truck traffic over the years. They would deteriorate just under the constant barrage of the trucks. The UHPC is much more robust and promises a much more robust system, and would therefore allow you to use these girders on major highways and not just small county roads. A couple of warnings here. The UHPC is flowable, as we've seen this morning. So you definitely need leak-proof forms, and I think it was Floyd who showed us what happens if you don't have a leak-proof form. If the deck is sloping, you may even need a top form so the UHPC doesn't bubble out the top at the low end of the joint. But again, these are things that you need to plan, and you can't just replace a conventional material with UHPC. These are a couple of pictures of tests on joints. And these are tests that we did back in 2017. And what we're looking at here is a 2-foot wide strip, which is basically a strip taken transversely out of a bridge. And it was planned to be one of these deck bulb tees. And this particular one is a 6-inch wide joint. We had a 1-inch end distance here, so we had a 4-inch overlap from there to there in these epoxy coated bars. And then number 5 bars. This is a picture of the test setup, and you should ignore this big diagonal steel thing here, and all that shows you is that our lab was extremely busy and full, so this was the only space we could find at the time. Rather, here is the panel. It's being held down at the 2 ends and pushed up in the middle, and the UHPC joint is in the middle here, and I'll tell you about this steel thing in just a second. We tested it this way up so that we could see the cracking pattern, which would therefore be on the top if you're pushing up from underneath, and it makes it a whole lot easier to see what's going on. This is looking down from on top of the panel after it had failed. And let's get rid of these guys first. The steel rods and the plates at the end, these are a lateral confinement system that we put on in order to try to simulate the fact that this joint is really not 2 feet wide, but if the girder is 150 feet long and this is a longitudinal joint, the joint should really be 150 feet long. And therefore, it would not be possible for this point to displace outwards in the real girder. So we held it in with a lateral confinement system of steel plates and rods. What you see here is this is actually a 5-inch joint. It's not the same as a 6-inch joint I just showed you with a 3-inch overlap. And the joint goes from here to here. These little buttons are sensors. And what you see has happened is that the failure happened actually between the UHPC here and the conventional concrete here. And that happened after the steel had yielded. And after yield, then the bars did start pulling out from the UHPC because they had such a short lap length, but not before we had cracked the conventional concrete back here. So this joint was actually narrower than what we finally recommended, but it was part of the parameter variation that we did. But as you can see, the joint itself has got almost no damage to it, very slight cracking here, but almost no damage to the joint itself of the UHPC. Well, if we look at design for durability, here we have an example which came from Michigan and was just recently constructed. And what they did was make steel tub girders with a UHPC deck, and they precast them and then they joined them together here. And we can look at the, here's a close-up. Here's the stay-in-place metal form deck. A total of 6 inches, 3-on-3. Here's the steel tub, and this is the 7-inch wide joint here. Here we've already seen this picture, but it's the same one again. Here they are actually casting. The steel tub is underneath, and here is the metal deck, which they're casting. And here they are putting them up in practice. And you can see that firstly, they've cast some conventional concrete just in the end here. It only extends in a couple of feet. And that was so they could make some connections between this girder and the adjacent one here. And you'll notice these are the joints, a pretty narrow joint with they only had a 3.5-inch overlap for the bars here. And here they are putting the UHPC joint in. I think we're coming up to time, so I'll try and move through these. I spoke to had contact with Dwayne Rogers from Michigan, and he reported to me that the total cost of the bridge was only $10,000 more due to the use of UHPC versus conventional concrete. And if you divide by the volume of concrete of UHPC, that was a premium of something like $600 a cubic yard. In his view, that was a real deal because recouping the $10,000 upfront premium would be pretty easy, just in reduced maintenance costs over the life of the bridge. So in his view, this is a perfect opportunity and he wants to do it again and again. He thinks it's a great deal. I note that there's only a 3.5-inch nominal overlap. And if we go back to this picture here, seems to me, I don't think that joint there is exactly the same width as this one. And maybe they were going to come back and move this unit over a little bit. But I think they might have got less than the 3.5-inch overlap there and more there. And my comment on that is that if you only have that small a nominal overlap, you need to be very careful in the placement tolerances, and it might be easier to use a slightly wider joint and have a slightly larger overlap. Well, I think our time is just about up, and so I would be very happy to answer any questions or refer them to somebody else if you have any. Thank you very much for your attention.
John, real good. We'll go on and get some questions. We've got some here. You there?
Yes, I am.
Yeah, you can get your camera on.
Put the webcam on for you. There we go.
Okay. I got here, what is stopping precast girder producers from running two separate lines in parallel, one for conventional concrete and one for UHPC?
That's a good question. I think the answer is money. What they would need to do is probably keep different bins of different material. And so you would have to have additional bins, some for the UHPC materials and some for the conventional materials. I think there's probably also the training question comes in as well, that if you have your staff in the production plant who are, if you train them to use UHPC and then next week they have to make regular girders, I think there might be some real questions of can they make that kind of switch, and are they going to make a mistake when they switch back to UHPC the week after? So I think there's some questions of training and questions of equipment which come into it.
Okay. Here's a question. How could we place concrete in a beam requiring 30 cubic yards without maybe getting a cold joint?
I think the first thing is 30 cubic yards would be a pretty big beam if it was UHPC, because what you would try to do, the 30 cubic yards, that's going to be costing you a fair amount of money. And I think what you would try to do is reduce the quantity, but you may come down and say, suppose you've got 15 or 20 cubic yards for a big long beam. I think that would potentially be a problem. And therefore you have to make sure that you've got big enough mixers, or you have two mixers that you can mix in parallel. And then you take a truckload from one and a truckload from the other and continue casting like that. And precast producers do it all the time with conventional concrete, but clearly with the greater mixing times needed for UHPC, that is one of the kind of logistical questions that you definitely have to work out.
Okay.
Could I add one more comment there?
Go ahead.
We got
Yeah.
time? Yeah, I believe that there's a guy called Vu in Malaysia who's been making UHPC girders for some time. And you might ask, well, how does he do it? Most of the ones that he does, I understand, are tub girders, and he makes them in fairly short sections and then splices them together using post-tensioning. And what that then means is each individual pour is less big than the 30 cubic yards that you're talking about. Okay. So that's his way of getting around it. He makes splice girders.
All right. Here's one. Would it be possible to make a girder with conventional high-strength concrete in the flanges and UHPC in the web for shear strength?
I have talked to a couple of precasters about that because I stole your idea, Paul. I thought it was a brilliant idea. I think, again, what the answers that came back to me were partly the ones about you've got to mix two different concretes at the same time, and there's a bit of a juggling act trying to make sure that they're each ready at the right time, especially because they have different mixing times. That would be one question. The other one would be, how can you ensure that you've got the right concrete in the right place, and that your joint between the two, the interface between the two, you'd probably like to be horizontal at, should we say, the bottom of the web. And that, I think, will be another part of the problem. I think it could be done, and I think it may be a very good way to go, optimizing the use of UHPC. But I think it would take some quite delicate planning to make it work.
Okay. I was thinking about in the bearing areas where in the girders where you always seem to have problems sometimes. If you could somehow make that out of UHPC, and the rest of the girder would be conventional.
That would be fabulous, actually, because in the bearing area, they quite often will put a slight a recess with a little taper in it to accommodate the camber at the end of the girder. And I think 3 times now I've seen girders where they've got the taper the wrong way round. You can imagine where that story's going. But if you could prefabricate a UHPC section in that region, and then you could make sure you had it right before you cast the rest of the concrete, that would be terrific.
Okay. Is it better to use a shear key detail or just to roughen the face of the concrete at a joint between panels?
Well, I can't remember if Ben Graybill has a different opinion to me on that one, but he's coming up, so he can state his opinion then. And my own feeling is that you're better to just roughen the edge of the panels, and particularly if you do it with a retarder, that seems to be a pretty good way to go. And we've done some tests on those principles, and you can get phenomenal shear strength out of just a roughened surface. I think with a shear key, there's always a risk that you'll break off one of the little kind of the pieces of the shear key, and then you won't have much left. So that would be my preference, just to roughen it.
Okay.
In fact, in a test that we did that I showed you, we didn't even roughen it. We said, let's do the absolute minimum and do nothing. And we never had anything that looked remotely like a shear failure.
Okay. Our time is just about up. I'm going to ask Don Diggemine to help me if we've got any questions that came in during the Q&A. Don?
Yes.
Thanks, Paul. John, there's a question from the audience. In terms of potential benefits that could be offered by UHPC, it says you didn't consider the fact that UHPC will have a lower carbon footprint than conventional concrete with respect to the life cycle analysis. What is your thoughts on this?
I think it's a great advantage. Yeah, we should absolutely do it.
Got one more from the audience. FHWA is recommending UHPC for partial depth overlays. How are they overcoming the boundary stress and electrochemical reactions?
I think that FHWA is coming on to talk in Module 5. I think we should ask them.
Well put. And I think that's our time up. John, great presentation. Mary Lou, back to you.
Thank you, John.
Okay.
Thank you, Mary Lou.
Thank you very much. Thank you, Paul and Don. We're now at the end of the fourth 40-minute module. Thanks again to John for presenting the module.